Okay, we now have defined the slope of a curve, y equals f of x, at some given point, a particular point when it exists. And we call it the derivative of f at c. So this is sort of a new word, right? We were calling it the slope of f at this point c. But to generalize this idea, we want to really think about the slope of the tangent line to the graph, y equals f of x, at a general point x, right? So in other words, I don't want to have to find the slope of a function at one point and then have to work through that whole limit definition all over again to find the slope at another point and then at another point and another point. I want to do this in general. I want to do this at a general point x. So in terms of x. So I'm expecting an answer in terms of x, right? I want a function defined in terms of x. And this function will take in as its input, it'll take in an x, and it'll output the slope at x, right? So it's a function. And what is this function? It's called the derivative function. And it looks identical to the definition of a derivative at a point, except instead of defining the point at c, we're just going to define it in terms of x. Okay, this notation right here is one of the notations that means derivative, and we pronounce it as f prime. So I would read this as f prime of x is equal to the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. You'll notice that always direct substitution of 0 for delta x is going to give me f of x minus f of x, which is 0 over 0. So we're always starting with a limit that's of indeterminate form. It's going to require some algebra, some manipulation in order to evaluate. Okay. Just a comment here that the domain of f prime, the derivative, will be all of the places where this limit exists, right? So wherever the derivative actually is defined, wherever this limit is actually defined. Okay, so this derivative, this slope-producing function, right, that's what I was trying to get at here, that the input takes in an x, the output spits out the slope. This slope function is the most important concept of this course. So I said this last class, and I just want to emphasize this again. This is huge. This is important. So I want to make sure you really understand this definition. I mean, this is, if you walk away from this course and you don't understand this definition, I have failed you as a teacher. Okay, so you have to really understand that this really comes down to the definition of slope. So explain why this derivative function, this so-called slope function, why is it, what does it have to do with slope? What does this crazy looking, slightly intimidating, notationally cumbersome formula have to do with slope? So remember that the slope between any given 2 points, and we talked about this last class too, but I want to just emphasize it. The slope between any 2 points is to find the change in the y coordinates over the change in the x coordinates, right? So what we're doing in this process of finding the derivative is we're starting with a point x, f of x, right? Some point we want to find the slope at. And then we're just moving some small little x over, some delta x over. So we're starting at x and we're just creeping over just a tiny bit, delta x. And we're evaluating the point at the function at that new point. So we want to find the slope. So originally the slope would be change in y coordinates, so f of x plus delta x minus f of x, right? That's y2 minus y1 over x plus delta x minus x. But what we want to do to find the slope at a single point is to let that delta x go to 0 so that the 2 points are in fact coinciding. And when we cancel out these x's, we see that in fact this is the definition of the derivative. So this definition really still is rise over run as we know and love it. Okay, so it's the same thing.